Welcome to our second review session for intermediate algebra. Today we're going to focus on an introduction to graphing and to functions. So if you are logged in, you can go ahead and type your name in the chat field. If you're using your cell phone, look at the very bottom of your screen. There should be a small bar for the chat that you can type your name in. We just want to get to see who's out there, who's watching us today. And if you're not logged in, then that's okay. Maybe write your questions down, bring them with you to class. So looking at sections 3.1, 3.2, 3.3, and 3.7, we start talking about graphing and in general looking at the basic technique of graphing, which is making a table of values. We start looking at some new types of equations, and then we shift gears and start learning about functions. Functions is a really important broad concept in algebra, so we want to make sure that we really understand the concepts of the functions, and we can carry that with us when we start learning about specific families of functions. So for this first example, we want to determine whether or not the equation is linear. Then we want to graph it. Now, to determine if it's linear, there are a few requirements. The first requirement is that it fits the form y equals mx plus b. That's our slope-intercept form. A second requirement is that it has a constant rate of change, which is our slope. And the third is that the graph is a straight line. So taking a look at the example that we have here, y minus x equals 8, let's first see if we can write this in slope-intercept form. So y minus x equals 8. If I add x to both sides, we get y equals x plus 8, which is in that slope-intercept form. So just looking at the equation, we can verify that yes, it is linear. Since I know that it's linear, I know that the graph is going to be a straight line. This process of recognizing the type of equation and then knowing what the graph is going to look like is going to help you when you're developing skills for graphing. Now we want to graph this. Using just a table of values, I'm going to select a default set of x values, -2, -1, 0, 1, 2. Now, these are just a sample set of x values. You can choose whatever x values you want. As you learn more about graphing, you'll find that some x values work a little bit better. And as we see in an example in a few minutes, sometimes we need to just continue to plot more points to make sure that we get the picture that we're looking for. When I plug in x equals -2, -2 plus 8 is 6. -1 plus 8 is 7. 0 plus 8 is 8. 1 plus 8 is 9. 2 plus 8 is 10. So that gives me 5 points that I can graph. -2, 6 is right here. -1, 7. 0, 8, 1, 9, 2, 10, and we can see that this graph makes a straight line by connecting those points. Now at this point you may already have some other techniques for graphing a line, say by starting at the y-intercept and using the slope. It really doesn't matter what technique you use. The process of making a table of values is kind of the fundamentals of graphing. So if you get stuck on a question that's asking you to graph, go back to making a table of values. As long as you can plug in an x value and evaluate the equation correctly, then you should be able to get some points and then hopefully come up with an accurate graph. Y equals x squared plus 3. Is this equation linear? Does it fit that model y equals mx plus b? The answer is no, because of that x squared. So this is not linear. In fact, this particular type of an equation is called a quadratic equation because of that x squared term. Now, when we see these equations, we should start recognizing the shape of the graph. And the shape of the graph is going to be a parabola, a U. So when I see an equation that has that x squared term, my thought process should say, okay, this is a quadratic, and I know what the graph is going to look like. It's going to look like a U. So when I start selecting X values to plot, if I don't find that shape, then I need to either check my work or continue to plot more points. So we've got some people signing in. I have a message that the audio is working. Whether or not the audio is working, I can't hear. Pablo, maybe you can confirm. Are you able to hear the sound? No. Okay, so we're having some issues with audio. Follow along, guys. See if you can just keep track of what I'm writing while we take care of that issue. So I'm going to select X values. Guys, also you might want to check to make sure that your computer is not set on mute, or if you're using a device that you don't have it on silent mode, that might be something you want to check. For graphing this, I'm going to select those same default X values, -2, -1, 0, 1, 2. And these are the X values that I'm always going to start with unless I have an idea that maybe I should start somewhere else. When we plug in -2, to show you the step, it's -2 squared plus 3. -2 squared is +4 plus 3 is 7. -1 squared is 1 plus 3 is 4. 0 squared is 0 plus 3 is 3. 1 squared is 1 plus 3 is 4. 2 squared, 4 plus 3 is 7. So when I go to plot these points, we have -2, 7, -1, 4, 0, 3, 1, 4, 2, 7. And I can see that these points are creating a shape that looks like that parabola. So I feel like I'm on the right track. Our next example, y equals the absolute value of x minus 1. Now this looks really similar to slope-intercept form, the y equals mx plus b, but that absolute value does something, it changes it. So because of that, it makes it a nonlinear equation. And anytime we have absolute value, it's not going to be linear. Pablo, I'm glad to hear that you got the audio now. When we see absolute value, you should be thinking and recognizing the shape that it's going to be, and that shape is going to be a V. So kind of thinking back, that last example, we were dealing with a quadratic equation, and the shape was a U. Anytime you end up with an equation that's quadratic with an x squared term, you're going to end up with that same shape. Now, the shape can change widths, it can flip upside down. Same thing with absolute value. When you've got an absolute value equation, you should expect a V, whether it's narrower or wider, whether it opens up or down. That will depend on some other components of the equation, but you should know the general shape going into the graph. So let's select some values for x and y. Now at this point I'm going to say, okay, I'm just going to pick a couple. Let me see which ones I want to pick. Let's pick -1, 0, 1. So I didn't feel like doing all 5 of those default values, but I got some negatives, I've got some positives. I think I'm okay. So let's plug this in. When I substitute in -1, we have the absolute value of -1 minus 1, which is the absolute value of -2, or 2. When I plug in 0, the absolute value of 0 minus 1 is the absolute value of -1, or 1. When I plug in x equals 1, the absolute value of 1 minus 1 is 0. So I'm going to stop here for a second and plot these 3 points. -1, 2, 0, 1, 1, 0. Now, if I look at these 3 points just the way they are, it looks like they make a straight line. And I'm thinking, wait a second, I know that this is an absolute value. I know that the graph is supposed to be a V. So I'm going to check my table as it is, and yeah, all of my points are correct. Since there's not an issue with me evaluating the points, maybe the issue is that I don't have enough points. So at this stage, we want to just continue to tack on some more x values until we see that curve turn back around to make that V shape. How are we doing on the sound, guys? If you're out there, I'm getting some mixed messages on our chat feed. So if you guys can let me know if you're able to hear us, I'd appreciate it. Thank you. So I'm picking some more values for x. Let's try 2 and 3. When I plug in x equals 2, the absolute value of 2 minus 1 is the absolute value of 1, which is 1. It's really clear now. That's awesome. Fantastic. When I plug in x equals 3, the absolute value of 3 minus 1 is 2. If I plot those 2 points, 2, 1, 3, 2, now I can see those points are starting to make that V shape. So with these 3 examples, we're just practicing making a table of values. We saw that sometimes we don't necessarily pick the best x values, which doesn't mean that we're doing it wrong, but maybe we just need to continue to plot more points. Are there any questions on graphing using a table of values before we move on to our next activity? Things to remember: plotting your ordered pairs, make sure you go x first and then your y. Those are some just real common mistakes. And always remember that you can always come back to this. Like I said, we're going to learn some new strategies for graphing that might be faster or might give us more insight to the relationship of the variables. But at this point, if you ever get to a question that's asking you to graph and you're not sure where to start, just start plotting points and see if that kind of turns on the light for you as to how it's supposed to look. For absolute value equations, I'm getting a question that says, do we need to always find the absolute value? Anytime we're dealing with questions that involve absolute value, yes, you do. Now, you want to make sure that you evaluate it according to the order of operations. The absolute value is a grouping symbol, so you have to simplify inside the absolute value before you take the absolute value. So I'm going to erase this just to show you what I mean. If I were to plug in x equals -2, because there's the absolute value there, it doesn't become +2 when I plug it in. We plug it in, the absolute value of -2 minus 1, and we want to evaluate what's inside the absolute value first. So this becomes the absolute value of -3, which is then 3. So Alex, I hope that answers your question. But yeah, anytime there's absolute value, you need to make sure you use that. If there is no absolute value, like the first 2 examples, then no, you would not use absolute value. Find the domain and range of each relation and then determine if the graph is a function. You'll notice that I don't actually have graphs here, so I'm going to sketch some graphs for us very quickly just to give us an idea. The first graph is going to look like this. Now, hopefully we recognize this is a linear equation. But let's talk about the domain and range of this and then whether or not it's a function. The last part, determining if it's a function, we use the vertical line test, and this clearly passes the vertical line test, so this is a function. And guys, this is my shorthand. If you haven't seen it yet, FXN is just quick note taking for function. For the domain and range, what we're trying to do is look to see where our graph is bounded. For the domain, we want to look at the x-axis. So if I think about this graph continuing on forever and ever in both directions, I'm not going to be able to bound it between any 2 values on the x-axis, which means the domain is going to be from -infinity to +infinity. For the range, we do the same thing, but now we're looking at the y-axis. So if I look at this y-axis and I'm thinking about the graph going, again, infinitely in both of these directions, there's no way to bound it from the top and the bottom where you're including the entire graph because it's always going to keep on going further. So that means that the range will also be from -infinity to +infinity. Now, anytime we have a linear function, which is going to be a graph of a straight line that also passes the vertical line test, anytime we have a linear function, the domain and range will always be -infinity to +infinity. For our second graph, let's sketch the graph of a parabola. Okay, so looking at this curve, Does this pass the vertical line test? Is this a function? And yes, it is a function. Now let's try to find the domain and range. The same way we did before, for the domain, we're trying to bound it on this x-axis. Since this continues forever and ever, think about my arms, it's going to end up being really wide eventually, right? So there is not going to be a limiting or a stopping point on the x-axis. So our domain is negative infinity to positive infinity. However, with the range for this graph, we can see that it is bounded, at least at the bottom, isn't it? If I look down here, the graph stops right there. It doesn't go beyond the x-axis. So the range is going to be from 0 and then all the way up to positive infinity, because it will continue to go up forever and ever. Guys, if there are any questions about domain and range, try to get those in now while we're working on the last example. Our last example, let's look at a graph that looks like this. So these are just real quick sketches to give us an idea. First, let's identify whether or not this is a function. If I consider the vertical line test, I can clearly see that this vertical line that I'm making with my cursor is going to intersect the graph twice, which means that it is not a function. Just because it's not a function doesn't mean that it has a domain and range, though. So let's find that. For the domain, again, looking at bounding on the x-axis, now we can see that we are bounded on the left-hand side of this graph. And then it goes forever to the right. So the domain representing that shaded region goes from 0 to positive infinity. For the range, thinking about these two endpoints going on forever and ever is going to be negative infinity to positive infinity. Be really careful when you're setting up your intervals. Make sure that your intervals always go from least to greatest. So negative infinity to positive infinity. Or in this second example, don't look at the shaded region as top to bottom. Look at it from bottom to top. So 0 to positive infinity. Decide whether the equation is a function. With a graph, it's really easy. We use that visual cue of the vertical line test. But when we have an equation, we actually have to test whether it's a function by verifying the actual definition of a function. And that is that every x has exactly one y. So what we want to do is test a couple of values of x to see what types of outputs we get. So I'm going to make my x and y table over here. I'm going to start with just a variety of numbers. So let's try negative 2. That gives me 1 over negative 2 minus 3, or negative 1/5. That's all I get. I don't get another answer when I plugged in negative 2. Let's try 0. 1 over 0 minus 3, that's negative 1/3. Still only getting one y value. Now I might want to try one other x value just to really confirm that I'm only going to get one y value out. Let's try 12. 1 over 12 minus 3 is 1/9. So again, I see that I only got one output for that particular x value. And these x values were completely random. I wanted to get a good variety of numbers, so I looked at some negative numbers, I looked at 0, and I also looked at positive values. But I'm pretty confident that no matter what I choose for x, I'm only going to end up getting one y value. Given the function, find the indicated values. So we have our function f of x, which is 2x plus 7. And we want to find f of 2, f of a, f of negative x, f of x plus h. So real quick, I have a question about the last problem that we looked at, so I'm going to go back. And the question was whether or not we always pick any values to plug in, and that's true. You can choose any x values. Like I was saying before, I wanted to make sure I had a good range of x values, so I looked at positive and negative and 0. But in terms of which values I picked, I just picked them at random. So it doesn't really matter. You're just trying to kind of give yourself that confidence that when you pick an x value, you're only going to get one y value out. And usually with 2 or 3 test values, you'll be able to determine that, yes, I'm only going to get one x value. One y value. Within those 3, if you were going to get multiple y values, you probably would have. Good questions. All right, so function notation. Remember this f of 2, this is not f times 2. Our context is indicating that this is function notation and that 2 represents our input. It's what we're going to plug into x. So plugging 2 in for x, this is 2 times 2 plus 7, or 4 plus 7, which is 11. Now, this concept of taking the value in parentheses and plugging in doesn't change just because we change what is inside the parentheses. In class, I gave an example of plugging in a smiley face or a heart, and we said it just means plug in the smiley face for x or plug in the heart for x. Whether that means anything to us doesn't matter. The task is always the same. You're always taking what's inside the parentheses and plugging it in for x. So I'm going to skip to negative x just so that we can get through all of our examples. This is 2 times negative x plus 7. 2 times negative x is negative 2x plus 7. So we see that when we changed from a number to a variable expression, we no longer got just a number out. So that's okay. All right, and as you learn more about function notation, you'll learn what that actually represents, but we're not going to get into that right now. And let's do f of x plus h. Again, just because what's inside the parentheses has changed, now it looks even weirder because there's 2 variables, it's still the same idea. We want to take x plus h and plug it in where we have an x. So that's 2. Instead of x, we've got x plus h plus 7. And this expression we can simplify by distributing the 2. So we get 2x plus 2h plus 7. As long as you continue to remind yourself what that function notation means, I suggest every time you see that problem, go through that dialogue with yourself. Plug in x plus h for x. That way you'll train yourself to think that way, and then you won't show up for the test thinking, oh, do I distribute the f here? Am I multiplying? What is the h? Where does it go? We don't want you to have any of that confusion when it comes time for the test. So just continue to remind yourself with that dialogue. Plug in x plus h for x. Plug in negative x for x. Plug in 2 for x. So in this example, we're still dealing with function notation, but instead of given the equation, we're given the graph and we're asked to find f of negative 1 and f of negative 2. Let's look at this real quick. F of negative 1. So the directions are saying find f of negative 1. What does that mean? Well, this whole thing is a y value. So what they're asking you to find is what is the y value when x equals negative 1? So to do that, we go to the graph. X equals negative 1 is right here, and then we want to go down to the graph. So we're actually looking at this point that I've highlighted in red. The ordered pair here is negative 1, negative 2. Now, that is not the answer. I'm not asking for the ordered pair. When I ask for you to find f of negative 1, I want the y value. So in this ordered pair, what is my y value? It is negative 2. Okay, so when I'm looking for f of negative 2, they want to know what is the y value when x equals negative 2. So going back to my graph, here's x equals negative 2, and I want to come down to the point on the graph that has that x value. You can see I've highlighted it in red on the screen. The ordered pair here is negative 2, negative 1. Again, the ordered pair is not the answer. Okay, I get this all the time when students get asked this question, find f of -2. They just want to put the ordered pair -2, -1, and that's only halfway there. We want to understand what this is actually indicating, that f of -2 represents just a y value. So the answer for f of -2 is -1. Graphing a linear function. So previously, I think it was the first example that we did today, we looked at graphing using a table of values, So I want to practice some of the other techniques for graphing a linear equation in the next couple examples. In this one, since it is in slope-intercept form, we want to use that. So our slope is the 1/3, which is your rise over run. And then the y-intercept is -2. So when I go to graph this, we're going to start with our y-intercept, which is at -2. And then we're going to use our slope to plot additional points. Since my slope is 1/3, that means I go up 1 to the right 3. If I go up 1 to the right 3, my next point is right there. When you're graphing a line, although you can technically graph a line with 2 points on your test, to make sure that your picture is nice and pretty and really straight, use the entire grid. So I'm going to go up 1 to the right 3 again. Now I've got all this space. If you can see my cursor, I've got all this space in the third quadrant that I haven't plotted any points. So I can plot points in the other direction just by changing both. Instead of going up, I'm going to go down. And instead of going right, I'm going to go to the left. 1, 2, 3. And we can see when we change that direction, we're still staying in line with those other points. Down 1, left 3. And with all of those points, it makes it really easy to draw a pretty nice straight line. And I'm drawing on glass, so if that means anything, that's a pretty good line. So we now have making a table of values to graph a linear equation, using our slope-intercept to graph a linear equation. And in the next example, well, actually, I'm going to jump down. In this example, we're going to graph the linear equation by finding the x and the y-intercepts. So we've got 4x plus 6y equals 12. To find the x-intercept, we're going to plug in 0 equals y, or y equals 0. So we have 4x plus 6 times 0 equals 12. 4x equals 12, and if I divide both sides by x, or by 4, x is equal to 3. So my ordered pair that I generated is 3 for my x, and my y value was 0. 3, 0 is right here. For my y-intercept, plug in x equals 0. The beauty of those two rules is that they don't change. When you guys go on to take college algebra, pre-calc, calc, so on and so forth, all of those classes you're going to be asked to find x and y-intercepts, and you use the exact same technique every single time. So we have 4 times 0 plus 6y equals 12, or 6y equals 12. Dividing both sides by 6, we get y equals 2. And now the ordered pair that we generated, we had an x value of 0 and a y value of 2. And we've got 2 points, which allows us to graph a straight line. Be very careful with this example, guys, when you're working on my math labs. If the question asks you to graph using the x and y intercepts, those are the 2 points that they want on the graph. If you use any other technique, say making a table of values or slope-intercept form, they may mark it wrong because what they're checking for are the correct x and y intercepts. We are out of time for today, which is okay. We didn't get to graphing inequalities, but if you guys need some more support on that, please let me know, or rewatch any of your lecture videos or the supplemental videos. Thanks to everybody who is watching right now and for the great questions you guys brought. We'll see you next time, and have a great week. Thanks, guys.